Okay, so the last speaker for the first session is Sohom Bhattacharya from Stanford University. So take it away.
Hello, everyone, and thanks for the invite. So today I'm going to talk about the upper and lower tail large deviation of the spectral edge in sparse random graphs. This is a joint work with two of my collaborators, Sohom Bhattacharya from Wharton and Shushantu Ganguly from UC Berkeley. Okay, so let's see what's the deal is about. So this is the broad goal of today's talk. Suppose you have a function which is from 0, 1 power n to r, and then you have a vector of n coordinates where each coordinate is like Bernoulli P and independent. And the objective that we have throughout the talk is to approximate this probability that f of y is more than its expected value by a factor of 1 plus delta. Always we will have this delta positive and fixed number. So this probability we want to approximate, and similarly we will want to approximate the lower tail probability, which is given by probability f of y is less than 1 minus delta times its expected value. So these are the two probabilities that we want to approximate. And we will give the rate and we will give the proper constants in our case. So what are the sort of f and y we will be talking about in this talk? So always think y as the adjacency matrix of a Erd graph, which will have n vertex, and every pair of vertex will be connected independently with probability p. So this will be our y. Now, what is the f? Now, there are various f's which has been popular in literature. One of the very prominent example is when we look at the subgraph count. That's what's the probability that in an Erd graph, the number of triangles exceeds its expected.
I can't see beyond the first slide.
Yeah. We're seeing just the first slide.
Like your name slide only.
Yes.
Really?
Yes.
Huh. Sorry.
It took me a while to figure out as well, but
okay.
Okay, now we can see things moving.
Okay. Can you see now?
Yeah, now we can see.
Oh, sorry. So yeah, so extremely sorry for that. So yeah, so just to go that we have a function f and we have vector y, and then we want to approximate the probability f of y is more than its expected value with a factor 1 plus delta. And what y we will have, it's the adjacency matrix of the Erd graph. And a popular choice in f in literature has been the subgraph count, which is the number of triangles exceed its expected value by a factor. But now we will talk about the largest eigenvalue of a graph, which is also a function of the adjacency matrices. So in particular, we will talk about not one, but rather finite number of top eigenvalues. Let's fix a number r, and we will look at the top eigenvalue lambda 1 to lambda r. And we will fix also the regime P in which we want to do the problem. So for the regime P, let's get back to one of the classical results, which has been like 20 years now. This Sudakov and Krivolovich paper of 2001 is the right reference for this, that the largest eigenvalue of Erd graph undergoes a change in nature, typically. That is, if P is much smaller than 1 over n times square root of log n over log n, then the largest eigenvalue is governed by the largest degree by the 1 plus smaller 1 and square root of the largest degree of the graph. However, otherwise, it's just governed by the NP. Now we will be interested in the first regime, where it's the largest eigenvalue has a connection with the largest degree. This is the regime where we will talk about the upper and lower tail problem. As one might expect, that this proof will rely on the large deviation of the extreme degrees, and as a byproduct of our result, we also get the upper and lower tail large deviation of the largest degrees of the graph in this regime. Okay, so let's see what happens to this largest degree value typically in this regime. So this is the situation here. The largest eigenvalue stays bounded if log n is smaller than a constant times log of 1 over np. And now comes the second regime where we will do the math. That is, if log n is much larger than log of 1 over np, but p stays still smaller than 1 by n square root of log n over log n. In this regime, the largest eigenvalue behaves like square root of LP, which is given by some number log n over log n minus log of np. Now, this is sort of a new result to get exactly hand of things, and reference would be a recent Anti-Noels and co-authors paper, which came out like 3 years back now. In fact, what I told you more is true. If you look at top finitely many largest eigenvalues, all of them has the same typical value, square root of LP in this regime. That is, if you look at top 100 large eigenvalues, so as n goes to infinity, all of them will be concentrated around square root of LP, the same value. Okay. Now, also our just one side note that our regime covers the constant average degree case, the C over N, which was of independent interest. And this was what got us interested in the problem in the first place. Okay. So with this notions, let's see what's the atypical probabilities that we want to talk about. It's this. We will have like we'll have R fixed, that is, we will look at R largest eigenvalues of the graph, and we will look at the upper tail event that all of them exceeds the a threshold 1 plus delta 1, 1 plus delta 2 up to 1 plus delta R times square root of LP. And similarly, we will consider the lower tail event that they're smaller than 1 minus delta 1 to 1 minus delta R. So we want to approximate the probability of this UTR deltas and LTR deltas. Okay, let's see what's the result here. So this is the situation of the upper tail problem. So before our work, it was known by a paper of 2 of my collaborators of this work. They showed in another work that if P is much larger than 1 over square root n, and if you look at R equal to 1, that is, we only look at the largest eigenvalue, then the upper tail probability behaves like e power minus a constant, then a rate of n square p square log of 1 over p. This is known as the mean field regime of the graph. And this constant is explicit. I have just hidden it for the purpose of talk, but they can get hand of like what's the constant here. This was known before. What do we show in our paper? We show that in the regime that we talked about here, if you take log of the upper tail probability and you scale by log n, then it goes to a constant, and the constant is explicit and it depends on all of the delta 1 to delta r's. And this is given by summation 2 delta a plus delta a squared. This is what we show. So it behaves like polynomially small. Now there is a very new work by Anirban Washak, which came on arXiv last month, which actually bridges the gap between the two regimes. There was a small gap in the regime when P was much larger than 1 by n squared log n and 1 by root n. And what happens there? He showed that when R equals 1, that is when we look at just the largest eigenvalue, then the upper tail problem undergoes a phase transition from sort of the mean field behavior to our sort of behavior when it's governed by the largest degree. And the change happens as n power minus 2/3 regime. But also, again, it's a result on just the largest eigenvalue and not like finitely many top eigenvalues. This is a very new result. Okay. And now let's see what happens in the lower tail. The lower tail sort of behaves quite differently. And what in fact happens is, like, if we go to denser regime than us, that is P is much larger than 1 over n squared log n over log n, then you can stretch P up to half. We don't even need P going to 0. Even up to the dense case, the largest eigenvalue at the lower tail behaves like e power minus n choose 2 times the Bernoulli entropy. Okay, so the constant, the Bernoulli entropy is given by IPX, which is x log x over p plus 1 minus x log 1 minus x over 1 minus p. So this is known as the replica symmetric regime. What do I mean by that? It means that if I condition that the largest eigenvalue is smaller than its atypical value, then the graph looks like approximately a Erd H random graph with a smaller edge density of 1 minus delta. So this is a behavior that only prevails in the lower tail, which was not the case in the upper tail anyway. Okay, but what happens in our regime? In our regime, we show that if we have log n is much larger than log of 1 over n pn, but p is smaller than 1 over n squared log n, that is the regime we are talking about, then the probability is really small and you have to take 2 logs and then you have to scale it by 1 over log n, and then we get the limit, which is 2 delta r minus delta r squared. So the first thing to note is that the constant does not depend on all of the deltas, but just delta r. But this is something that we also observed from the similar case in the, if we look at just the largest degree large deviations, this happens there, and one might expect that the same thing can happen here. And it happens. Now, the second thing is, why are the rates so very different? Now, this is something that one might expect from like other fields of this sort of theory in the large deviation of random matrices or populations, because in the upper tail problem, when you want to have an atypical event, you just want one eigenvector to be atypical, which is much more likely. But here, if you want the largest eigenvalue to be small, then you want all the, at least a bulk of eigenvectors to be like small, and which is much more rare event. And that's why you don't expect this to, in fact, happen that much frequently. So that's why the probability is much lower. Now I have like maybe 2-3 minutes. I would just briefly mention like how the proof of such a result will work. So in the upper tail problem, which was this, the proof goes basically as follows. We want to show that we want to get hand in the largest eigenvalues. So we want to show that the graph is essentially a tree. So these two steps show that the graph cannot have too many cycles to affect our atypical events. Now, once we show that this is the case, then in the next two steps, we actually show that not only it's a tree, we can see that it's actually essentially a star graph, and we can throw away all the other parts. So it's a 3-step pruning procedure where after that we get a star and we get something else which we don't actually care about. And for the star, the spectrum is explicitly known. And once we get hold of the star, we can compute the upper tail probabilities. And the lower tail idea is quite different. In fact, here we show a Ramsey type result, which says that there exists a K such that if the kth largest degree is large, then either the largest eigenvalue has to be large or the rth largest eigenvalue has to be large. And this contradicts our lower tail event. This is the broad idea. And of course, it's a small talk, so I will hide like every small details of this thing. And these are the basic ideas how we prove this thing. Now, let's see what are the open problems in this thing. First open problem is in the lower tail regime. Lower tail regime, the eigenvalue problem that we got gives a lower tail of λ1 to λr. But our proof technique doesn't give a lower tail eigenvalue for the marginal ones. If someone asks you what's the probability, the second eigenvalue is smaller than that, we do not get hold of that because of our proof technique. There is a gap, one might ask, and I think it's a good problem. And similarly, in the upper tail problem, the question still remains that what happens when we look at the p is much larger than n power half minus half. That's the mean field regime. Can we talk about the joint large deviation? That is, if I look at the first 5 top eigenvalues, can we talk about the upper tail? Now, there are guesses what type of structure will govern this, but there is no rigorous proof how one can get hold of this. With this open problems, let me just finish this talk and let me just stop share.